So the first problem that we had to solve was to state the chain rule. The chain rule is if f is differentiable at g of a and g is differentiable at a, then f g is differentiable at a and f g prime of a equals f prime g of a times g prime of a. And basically this is saying that it's going to be the outer function times, or the outer function with the inner function substituted in to the outer function times the derivative of the inner function. The second question was to derive a formula for the derivative of arctan of x using the rule for the derivative of an inverse function coming from chain rule. So I set it up the same way we did in the arc sine in class. So the derivative of the inverse is equal to 1 over f prime. So the derivative of the inverse. So the derivative of arctan of x, if we apply it to this equation up here, we can say is equal to dy tan y. And the reason it's y's here is because with an inverse, you exchange the x's and y's. So y equals arctan of x is equal to x equals tan of y. So that's why there's the y's here. So now we can say the derivative of tan y is going to be secant squared of y. So now this is 1 over secant squared of y. No, this is 1 over on here. And now, thanks to our Pythagorean identity, tan squared theta plus 1 equals secant squared of theta, we can substitute this with 1 over tangent squared theta plus 1. So we basically just put this in the bottom instead of this. And now, if we substitute the x for this tangent squared, we just get x squared. And that's the derivative of inverse tangent. Problem number 3 was derive a formula for the derivative of a composition of 3 functions at a point by using chain rule. So, using the same sort of mentality as we did in chain rule, I did d dx f of g of h of x. So these are going to be, h is the inner function of g, and g is the inner function of f. Now this is basically saying, to say it more explicitly, we can say f prime of g of h of x times g prime h of x times h prime of x. So each step we're getting closer and closer to this center function and finding the derivative. So if we separate this into 3 parts, here's our first one. we're taking the derivative of the outermost. Here we're taking the derivative of the innermost, or the second outermost, and here of the innermost. And then simply substituting in whatever the inner functions are at that time. So our fourth problem was to find the derivative of arc tan of e to the tan x at x equals 0 using a formula we used in the previous problem. So the formula we derived in the previous problem was f of g of h of x. And this basically translates to f prime g of h of x, g prime of h of x, times h prime of x. So we're just going outer to inner, taking the derivative of each following function. So first we're going to define f of x, g of x, h of x just to make it fit this form. F of x is going to be our arctan x. Our g of x is going to be our e to the tan x. And h of x is going to be our tan x. So the derivative of the first of f is going to be 1 over 1 plus x, which this is acting as x in this case, e to the tan x squared, times g prime of h of x, so the derivative of g with h plugged in, which this is h, so e to the tan x, times the derivative of the innermost, which is tan x, and secant squared x. So now we're going to find it more specifically. This is the derivative of arctan e to the tan x. Now we're going to find it more specifically at this point x equals 0. So d dx at x equals 0 equals 1 over 1 plus e to the tan 0. So I'm basically just plugging 0 into all our x's, squared, e to the tan 0, secant squared of 0. So now if we keep on calculating this, 1 over 1 plus tan 0 is 0, e to the 0 is 1 squared, e to the tan of 0, like we said, is 0, so e to the 0, and secant squared of 0 is the same thing as saying 1 over cosine of 0. So 1 over 1 plus 1 squared is half, e to the 0 is 1, and cosine 0 is 1, so this is 1, and our final answer is 1/2.